sort of forced expansion with an external pressure P1 into a second container at a lower pressure P2. So I want to say, for that process, what do we know about, in fact, let's not use differentials, let's use delta. Delta U is Q plus W. For an adiabatic process, if we manage to do this adiabatically, the heat is 0. So delta U and work are the same thing. The only changes in the energy of this gas come from the changes in work. And I've done some compression of the gas on the P1 V1 side, and I've done some expansion of the gas from this initial volume 0 up to a final volume V2. So any change in the energy, so final minus initial energy, must be related to the work of the gas. The work on the left, so I've got work is always minus P times dV, or delta V. On the left, so let's mark these on the left side, the external pressure was P1. The change in volume, I went from a volume V1 down to a volume of V0. So the change in volume was final volume minus initial volume. And then I can add to that the PV work on the right, external pressure in this case is P2, and the change in the volume in this case, I've gone from an initial volume of 0 to a final volume of V2. So my volume changes V2 final minus 0 for my initial volume, and I can rewrite all those. So I've got a minus P1 times a minus V1, and I've got a minus P2 times a V2. So that's equal to U2 minus U1. If I rearrange that equation just a little bit to get to 2's over to the left-hand side and the 1's over to the right-hand side, I see that U2 plus P2 V2, bringing these over to the other side. When I bring U1 over to the right side, it becomes positive, so I've got U1 plus P1 over V1. And this quantity, U plus PV, we know another name for the internal energy plus the PV product. That's just equal to the enthalpy. So on the left side, I've got U plus PV at conditions 2, in other words, the enthalpy at the final conditions. And on the right side, I've got U plus PV at the initial conditions, or the enthalpy at the initial conditions. So what that has just showed us is, despite the fact that I'm changing the pressures and the volumes, and despite the fact that some PV work is going on, the internal energy may be changing, but the enthalpy is not changing. The enthalpy of the system before and after the PV expansion is exactly the same, and that's sort of the point of enthalpy, remember, is to allow us to not have to worry too much about the PV work. So what we've just found is that this process, this not perfectly adiabatic expansion, but this forced expansion, compression and then expansion of a gas under adiabatic conditions, turns out to not change the enthalpy. So that's yet another type of process that we can give a name to. A process that doesn't have a change in the enthalpy is called an isenthalpic process, like isoenthalpic process. So if we're interested in the temperature change of a gas, so I mentioned a minute ago that if I did this for an ideal gas, we would see no temperature change. But if I did this for a real gas, if I stick oxygen or nitrogen or carbon dioxide or something in this container and perform this process, we do in fact see a little bit of cooling. And the reason that's true is because real gases are not ideal gases. Real gases do have some intermolecular attraction between them. So let's say if I take, at this higher pressure, the gas molecules are relatively close together. It's still a gas, so they're not terribly close together, but they're closer together than they are at P2. At P2, the gas molecules are at a lower pressure, so they're farther apart from one another. For an ideal gas, they don't care how close together they are. Their kinetic energy is just determined by their internal energy and vice versa. But for a real gas, they do have some potential energy, and they attract each other. So molecules that are close together are attracting each other, have some favorable negative potential energy. If I expand the gas and make those molecules get further apart, then I've had to move against that attraction. I've had to put some energy in to increase their potential energy, so their potential energy goes up as I do that expansion.